In this lecture, we're going to use the procedure derived in the previous lecture to calculate the least squares estimators of the beta parameters for a simple linear regression model. And we're going to do it in the context of example 2.1 in the text, which deals with the relationship between shear strength and age of a rocket propellant. We'll do this by solving the normal equations for the model, the solutions of which are the least squares estimators of the two beta parameters in the simple linear regression model. We'll solve the normal equations using three approaches. First, by solving the system of equations by hand via algebraic manipulation of the equations in the system. Secondly, by hand using Gaussian elimination with Jordan reduction of the augmented matrix for the system. And thirdly, via Gaussian elimination with Jordan reduction of the augmented matrix for the system using the TI-84 calculator. So here's an outline of what we'll be looking at in this lecture. We'll first remind ourselves of the normal equations for the simple linear regression model. We'll then look at example 2.1, called the rocket propellant data in the text. We'll look at finding the least squares estimators for model parameters by solving the normal equations. First, we'll solve them by hand using algebraic manipulation of the equations in the system. The second method we'll use is to solve the normal equations by hand via Gaussian elimination with Jordan reduction of the augmented matrix for the system. Thirdly, we'll solve the normal equations via Gaussian elimination with Jordan reduction using the TI-84 calculator. We'll then summarize our results and interpret them. We'll also look at some additional important questions that are natural follow-up questions to the analysis. And from these additional questions, we'll see that estimating the regression function is just the first step in an analysis. There is much more work to do beyond point estimation. So let's first review the normal equations associated with the simple linear regression model. The normal equations associated with the simple linear regression model were derived in the previous lecture video and are given by the two equations shown here. So the first equation, beta 0 hat times n, the sample size, plus beta 1 hat times the sum of the x's, has got to be equal to the sum of the y values. In the second equation, we have beta 0 hat times the sum of the x's plus beta 1 hat times the sum of the squared x's. That has got to equal the sum of the products of the corresponding x's and y's. Now, this system of equations, comprising the normal equations, involves the two beta parameters as well as a number of summary statistics. Once the data have been observed, we can calculate those 5 summary statistics, again being the overall sample size, the sum of the x's, the sum of the x squared values, which is also called the uncorrected sum of squares of the x's, the sum of the y values, and then the sum of the products of the corresponding x and y values, which is also called the uncorrected sum of products. Once we've calculated these summary statistics, they can be substituted into the normal equations, which then become a system of equations involving only two unknowns, beta 0 hat and beta 1 hat. And so we can solve that system of equations, that system of two equations in two unknowns for beta 0 hat and beta 1 hat. And those values are the least squares estimators of beta 0 and beta 1, respectively, because they satisfy the least squares criterion. So once we have observed the data and calculated those 5 summary statistics and plugged those summary statistics into the normal equations, how can we solve the normal equations for beta 0 hat and beta 1 hat? Well, there are a variety of approaches, including numerical trial and error, algebraic manipulation of the equations in the system, and then finally, a Gaussian elimination with Jordan reduction of the augmented matrix for the system. Now, in this lecture video, we're going to be focusing on the last two approaches, algebraic manipulation of the equations in the system and Gaussian elimination with Jordan reduction of the augmented matrix for the system comprising the normal equations. We're going to apply this to example 2.1, the rocket propellant data. And so here is a description of the situation. A rocket motor is manufactured by bonding an igniter propellant and a sustainer propellant together inside a metal housing. The shear strength of the bond between the two types of propellant is an important quality characteristic. It is suspected that shear strength is related to the age in weeks of the batch of sustainer propellant. An engineer measured shear strength, which is the response variable y, in psi, and age, which is the explanatory variable x, measured in weeks, on 20 different batches of propellant in order to understand and quantify the relationship between shear strength and age. The data are shown on the next slide. And so here we have our 20 observations. We have shear strength, which is the response variable, measured in psi, and the age of propellant, measured in weeks. That's the explanatory variable x. So why don't you pause the video for a few moments and just visually inspect the data and see what you can discern about the relationship between shear strength and age by visual inspection. So having looked at the data, what can you detect from visual inspection of the raw data? Are you able to discern whether two measurements are related? If you can detect that the two measurements are somehow related, are you able to discern the nature of that relationship? In other words, whether it's increasing or decreasing. In addition, if you are able to discern whether it's increasing or decreasing, are you able to go further and determine whether that relationship is linear, perhaps quadratic, maybe even higher order, or maybe there's a reciprocal relationship, or perhaps some other type of relationship? If you can do all that, can you go even further and quantify the relationship? That is, to put numbers to it. These questions have been arranged from general to specific, from the easiest to answer to the more difficult to answer. This is the natural progression of the types of questions researchers and data analysts ask about and from data. Now, admittedly, it's difficult to tell much, if anything, from merely staring at the raw data. To answer these questions, the data need to be subjected to various forms and levels of statistical processing. Now, a good first step when looking for a relationship between two measurements is to create a scatter plot of the data. This is shown on the following slide. So here we have a scatter plot of the data with shear strength, the response variable y, on the vertical axis, and the age of propellant in weeks, this is our explanatory variable x, on the horizontal axis. So stop the video for a few moments and just take a look at this scatter plot and see what you can figure out. The scatter plot reveals a decreasing trend between shear strength and age. That is, as age increases, shear strength tends to decrease. In addition, over the range of ages observed in the data, the relationship would appear to be well approximated by a linear function. Therefore, a simple linear regression model relating shear strength and age of the form y equal to beta 0 plus beta 1 times x plus epsilon, which is the canonical form of the simple linear regression model, would appear to be reasonable. As the old adage says, a picture is worth 1,000 words, or in this case, around 50. So a simple linear regression model appears to be appropriate for these data. So let's find the least squares estimators of the simple linear regression model by solving the normal equations. The first step in finding the least squares parameter estimators is to calculate the summary statistics involved in the normal equations. And so I've calculated those summary statistics and presented them here. These can then be plugged into the appropriate locations in the normal equations, which are given on the next slide. Now this system contains two equations in two unknowns being beta 0 hat and beta 1 hat. And this is easily solved by hand. Now, in case you're a bit rusty solving systems of equations, the next several slides demonstrate how it's done. And so let's look at solving the normal equations by hand via algebraic manipulation. The first step is to get rid of one of the variables. So dividing the first equation by 20 and the second equation by 267.25 gives the following equivalent system of equations. And so we see those two equations here. This system of equations is equivalent to the first because it has the same solution set. Now notice that by dividing equation 1 by 20 and the second equation by 267.25, the two equations now have beta 0 with a coefficient of 1 in both equations. The second step is to reduce the system to one equation involving the other variable. So subtracting the second equation from the first equation yields a single equation with one unknown, the unknown being beta 1 hat. So by subtracting equation 2 from equation 1, beta 0 hat disappears, and so we have one equation remaining with one unknown, beta 1 hat. The third step is to solve for that variable. So we're going to solve for beta 1 hat by dividing both sides of that equation by negative 4.14054,022. The value we get for beta 1 hat turns out to be negative 37.15359104. The fourth step is to solve for the variable removed in the first step. The variable removed in the first step was beta 0 hat. And so we plug the value that we now have for beta 1 hat into either of the original two equations and then solve the resulting equation for beta 0 hat. And when we do that, we get beta 0 hat equal to 2,627.82236. So the solution of the normal equations is given by beta 0 hat equal to 2627.82236 and beta 1 hat equal to negative 37.15359104. These are the least squares estimators of beta 0 and beta 1 respectively. And so the least squares estimate of the simple linear regression line is given by y hat equal to beta 0 hat plus beta 1 hat times x, which is 2627.82236 minus 37.15359104 times x. Next, we're going to solve the normal equations by hand via Gaussian elimination with Jordan reduction of the augmented matrix for the system. So here is the augmented matrix for the system. We have this 2 by 3 matrix, 2 rows and 3 columns. And the entries in this augmented matrix correspond to the quantities, the coefficients on beta 0 hat and beta 1 hat on the left-hand side of each of the two equations, and then the constants on the right-hand side. Now, the following slides show the operations to transform the augmented matrix to what is called reduced row echelon form using Gaussian elimination with Jordan reduction. And these operations correspond to the same type of operations, the algebraic manipulations we did previously in solving the system. So step 1 says, and you will read along in the description below, the notation above is the shorthand way of representing this, but in words we would say that we're going to multiply the entries in row 1 by 1 over 20 and retain those values in row 1. Similarly, we're going to multiply the entries in row 2 by 1 over 267.25 and retain those values in row 2. And so we see on the left-hand side we have the initial augmented matrix, and then on the right-hand side, to the right of that right arrow, we have the transformed matrix after we perform those two operations in this first step. Now the second step says to subtract row 1 from row 2 and replace row 2 with the resulting values. And so if we subtract the 1 in row 1 from the 1 in row 2, we get 0. Subtracting 13.3625 in the first row from the 17.503.04022 in the second row, you can see we get 4.14.054.022. And then subtracting the 2131.3575 from the 1977.521.562 yields negative 153.835938. Step 3 says to subtract 13.3625 divided by 4.14.054.022 times row 2 from row 1, and then replace row 1 with the resulting values. And so again, we've got the matrix that resulted from the previous step on the left-hand side here. And after we perform this operation, we see the resulting matrix on the right-hand side of that arrow. And then step 4 says to multiply the entries in row 2 by 1 over 4.14.054.022 and retain those values in row 2. All right, so the resulting matrix from those 4 steps is this 2 by 3 matrix here. That is the augmented matrix for the system of equations shown at the bottom of this slide, which is equivalent to the original system of equations, that is the normal equations, and therefore has the same solution set. Now, the great advantage of this system of equations over the original normal equations is that the solution can be read directly from the system, right? The system shown here is beta 0 hat equal to 2627.82236, and beta 1 hat is negative 37.15359104. And so that is the solution of this system of equations, and this system of equations is equivalent to the original normal equations, and so the solution to this system is the same as the solution of the normal equations, and so these two values solve the normal equations. And so again, these two values are the least squares estimators of beta 0 and beta 1 respectively, because they satisfy the least squares criterion. Next, we're going to solve the normal equations via Gaussian elimination with Jordan reduction on the TI-84 calculator. Gaussian elimination with Jordan reduction is relatively straightforward to do by hand, at least for simple linear regression. It can also be performed on a calculator such as the TI-84 calculator using their reduced row echelon form function. How to do this is shown on the next several slides. So here is a graphic of the TI-84 calculator. And I've got the statistics button highlighted here. And what we're going to do is press that button, and it's going to get us into the statistical mode for the calculator. And it's going to allow us to enter the data into two lists. And so I've already done that, and I'm showing screenshots here of the TI-84 emulation software. And so you can see that I've entered the values for X, age, into list 1, and I've entered the values for Y, or the shear strength, into list 2. Now, the first thing we need to do once we get the data into the calculator lists is to calculate summary statistics for the two variables. And so I'm going to press the stat button on the calculator. That will get me to this menu in number 2 on this slide. And we can, from here, from this menu, select what to do. And we want to, at this point, calculate two variable statistics. All right, that will generate the third screen. And so we see here that we've got two variable statistics. And these various summary statistics are populated in the statistical memory of the calculator. So the calculator is keeping track of the sample size. It's keeping track of the sum of the x's, the uncorrected sum of squares of the x's, as well as the sum of the y's, the uncorrected sum of products of the x's and the y's, and so forth. All right, then we want to put the appropriate summary statistics into a 2x3 matrix that represents the augmented matrix for the system of normal equations. And that functionality is found by pressing the second button, and then the button shown highlighted in red here, which in blue above the button says matrix. And when we do that, we're going to be presented with the matrix menu. And so we see here that we can select the names of various matrices. We can perform various math operations on matrices. But the first thing we need to do is we need to edit a matrix and specify its size, its dimensions, and then enter the values of those summary statistics. So we would use the arrow keys on the calculator to highlight the edit menu in this page. And once we do that, we can select we'll just use the A matrix here. And we would specify that the A matrix has 2 rows and 3 columns. That's the size of the augmented matrix for this system. All right, and then once we do that, then we can plug the values for those summary statistics into the appropriate locations in this matrix. Now, let me just say that I would not recommend writing those summary statistics down and re-entering them by hand. Instead, what I would recommend is using the vars key on the calculator to select the various summary statistics that are already saved in the calculator memory and plug those values into the appropriate locations in the matrix in that way, because then you'll have the most precision available in those values. Then we're going to press second and matrix again, and then we're going to use the right arrow key to select the math menu, and then toggle down or arrow down until we see the RREF function. Select that, and then again press the second and matrix key, and then under the names option, select matrix A, select that, and then enter a right parenthesis. Once we do that, press the enter key, and it will perform Gaussian elimination with Jordan reduction on the augmented matrix and display the reduced row echelon form of that matrix as shown here. This system shown here, the reduced row echelon form, corresponds to the augmented system beta 0 hat equal to 2627.822359 and beta 1 hat equal to negative 37.15359094. So that's what we got before as well. Okay, next we're going to show how to get a scatter plot of the data with the least squares regression line superimposed over the data. And so the first step would be to press the y equal to key in the upper left part of the calculator, and from there you'll be able to enter the equation of the least squares line for that particular function. We would then press the window key and plug in dimensions for the viewing window to make sure that all of the data points can be viewed on the screen at one time. And so here is what this looks like when we go through this process. So we've entered the equation for the least squares line for y1. We then pressed second and y equal to get to the stat plots menu. We've turned plot 1 on, and then you can see here for the type we've selected the first type of plot, which is a scatter plot of the data. All right, and in the fourth window here, you can see the dimensions that I've used for the display window to make sure that all of the data can be displayed on the calculator at once. And then once we press the plot button, this is the scatter plot that's displayed. So we have a scatter plot of the data with the least squares line superimposed over the data. So here's another view of that type of plot, a scatter plot of the data with the least squares line superimposed over the data set. And we see here that we've got the equation of the least squares line up there in the upper left corner, and it's displaying those quantities rounded to a certain number of decimal places for each of those estimates. So let's summarize the results and interpret them. So we've determined that the relationship between the shear strength of the bond between the igniter and sustainer propellants in a rocket motor and the age of the propellant is decreasing in nature, meaning that as the propellant in the rocket motor ages, the shear strength decreases. In the interval over which ages were observed, which ranged from 0 to 25 weeks, the relationship is well approximated by a linear function. The regression line relating the response variable shear strength to the explanatory variable age was estimated to be y hat equal to 2627.8 minus 37.154 times x. This is the estimated line obtained using SSE, the sum of squares error, as the criterion function. Minimizing SSE is called the least squares criterion. Note that at any particular point in time, shear strength varies from one sample to another. The estimated mean shear strength of all samples of a particular age is denoted by mu hat sub y given x, as well as by the expected value of y given x. And I should have a hat on that expected value, so I will correct that in your notes. All right, and this is given by the estimated regression equation shown here. So mu hat sub y given x is equal to, and then you can see here I do have the hat on my expected value here. So the estimated expected value of y given x, which is equal to beta 0 hat plus beta 1 hat times x, which again is equal to 2627.8 minus 37.154 times x. So again, that is the estimated mean shear strength of all samples of a particular age. Now, the predicted shear strength for a particular sample or individual sample with a particular age is given by the estimated regression equation, y hat equal to, and then the estimate of beta 0 plus beta 1 times x, that is the estimate of the deterministic part of the model, and that too is equal to the same quantity as above, beta 0 hat plus beta 1 hat times x, or 2627.8 minus 37.154 times x. And obviously we're rounding to a certain number of decimal places here. The estimated mean shear strength of all samples of newly prepared propellant, that is, at age equal to 0, is equal to the estimated regression equation evaluated at x equal to 0. That is, mu hat sub y given x, where x is equal to 0, is equal to the estimate of the expected value of y given x equal to 0, and that is equal to beta 0 hat plus beta 1 hat times 0, which is 2627.8 psi. So that 2627.8 psi is the estimated mean shear strength of all samples of newly prepared propellant. The predicted shear strength for a particular individual sample of newly prepared propellant, again at age equal to 0, is equal to the estimated regression equation evaluated at x equal to 0. In other words, y hat, the predicted value of the response for a single observation, is equal to the estimated value of the deterministic component evaluated at x equal to 0. That is, as above, beta 0 hat plus beta 1 hat times 0. All right, and that again turns out to be 2627.8 psi. So that is also the predicted shear strength for a particular individual sample of newly prepared propellant. For every 1 week increase in the age of a propellant, the expected decrease in shear strength is estimated to be 37.154 psi. So these are the things that we can conclude about the relationship between shear strength and age thus far in our analysis. Here are a few caveats. The approximate linear relationship between shear strength and age cannot be assumed to hold for propellants greater than 25 weeks in age. All of the preceding statements are applicable only to propellants for which age is no more than 25 weeks. And so the estimated regression line should not, and I repeat not, be used to make inferences or predictions about the shear strength of propellants for which age is greater than 25 weeks. In other words, the estimated regression line should not be extrapolated beyond 25 weeks. Okay, here are some additional important questions. How could we construct a 1 minus alpha times 100% confidence interval estimate of the average shear strength of all samples of a given age? Now, this would be a confidence interval estimate of mu sub y given x, which is also the expected value of y given x. Second, how could we construct a 1 minus alpha times 100% prediction interval of the shear strength for a particular individual sample of a given age? This would be a prediction interval for the response y of an individual experimental unit with a given x. How could we construct a 1 minus alpha times 100% confidence interval estimate of the expected decrease in shear strength for each 1 week increase in age? Now, this would be a confidence interval estimate of beta 1. And finally, how might we perform alpha level hypothesis tests about the expected decrease in shear strength for each 1 week increase in age? This would be an hypothesis test about beta 1. Solving the normal equations for a given set of data using Gaussian elimination is sufficient for calculating the values of the least squares estimators. But a complete statistical solution involves much more than mere point estimation. It involves testing hypotheses about model parameters and constructing confidence interval estimates of them. And to do these things requires knowledge of the joint and marginal sampling distributions of the least squares estimators beta 0 hat and beta 1 hat. In order to obtain this information, we will need to use the normal equations to derive formulas for beta 0 hat and beta 1 hat. And that will be the topic of the next lecture. So we see that estimating the regression function is just the first step. It's just the beginning of our analysis. There is much more work to do. And I'll see you in the next lecture video.